Section 3.4a, Symmetry. Our objectives are to determine whether a graph has y-axis, x-axis, or origin symmetry, and to determine whether a graph of a function is even, odd, or neither. First, we're going to look at tests for symmetry. Symmetry with respect to the y-axis is also known as an even function, and we'll talk about that in a little bit. The coordinate test is if you have xy as a point on your graph, then you also have to have negative xy on the graph. You have to have both. The algebraic test is replacing the x values with negative x. If you get an equivalent equation back, then it means it does have y-axis symmetry. So looking at these equations that we have here, we want to determine algebraically, and it should say if the function has y-axis symmetry. So if I look at this equation, the way that I would determine that is by taking out my x values and replacing them with negative x. If we get an equivalent equation, then we know that it does have y-axis symmetry. If not, then it would not. So I'm going to always put whatever I plug in for x into parentheses. When I do that, if I simplify my equation, now I get y is equal to negative x to the fourth power would take care of that negative that we have, and it's really equal to then x to the fourth power, so that's the same. And then the negative x squared, again, same thing, a negative number squared or to an even power is going to end up being positive, so that gives us 5 minus 5x and then plus 3. Notice that this equation here is the same as my beginning equation. Because of that, then I would say, yes, it has y-axis symmetry. So let's go ahead and do the other equation. So for this other equation, I would do the same thing. Replace x with negative x. If we get an equivalent equation, then we know we did it correctly. So negative x squared is just x squared plus y squared equals 1. I got the same equation back that I started off with. So again, yes, we have y-axis symmetry. And if you kind of think about the question a little bit, you would notice that the only time that we wouldn't get the same equation back when we plug a negative x in is if we had our x value to an odd power, which is why that we say that y-axis symmetry is for even functions, because when you plug negatives in for x and you square them or take them to an even power, it gets rid of the negative, so that would make us have y-axis symmetry. So the next part, it says complete the graph so it has y-axis symmetry, and remember that means we have to have both xy and negative xy, so I have 0, 0 here, so that stays the same. If I have 1, 1, I would have to have negative 1, 1. If I have 2, 2, I'd have to have negative 2, 2, and so on and so forth. And then I would get my ruler out and draw my line. And now this graph right here has symmetry with respect to the y-axis. So if I were to fold it in half along the y-axis, you'll notice that both sides would match up to each other. The next thing that we're going to look at is symmetry with respect to the x-axis. The coordinate test is if xy is a point on the graph, then you have to have x negative y on the graph. So this is opposite from the last problem that we did because you replaced x with negative x, now we're replacing y with negative y. And the algebraic test, again, replace y with negative y. If it produces an equivalent equation, then we know that we have symmetry with respect to the x-axis. So looking at my equations here, I'm going to replace y with negative y. And always put it in parentheses when you're plugging in a number. When I simplify this, negative y to an even power is just going to be the same thing. Notice that here and here, the equations are the same. So yes, this has x-axis symmetry. And if I look at number 2, and again, same thing, everywhere I have a y, I'm going to replace it with negative y. If I get the same thing back, then I know that I have x-axis symmetry. So negative y squared would become still positive y squared. And then now I have y to an odd power, which means negative negative becomes positive y equals 0. Because of this is a negative and this is positive, that means that we did not get an equivalent equation back, so this does not have x-axis symmetry. And this one does have x-axis symmetry. So looking at the graph, it says complete the graph so it has x-axis symmetry. So if we have the point xy in my graph, remember we have to have x negative y, so 0, 0 would stay the same. If I have the point 1, 1, I would have to have the point 1, negative 1. If I have the point 2, actually let's do 3, 4, so let's do 4, 2, which is right here. Then I have to have the point 4, negative 2. And then I would draw my line. And it looks like I did that a little bit off there. I should have moved it down a little bit further to here. There we go. And this means that if I were to fold my graph along the x-axis that we have here, my graph from the top part here would match up with my graph on the bottom part there. And that would mean that we would have x-axis symmetry. The next test that we're going to talk about is symmetry with respect to the origin, and origin functions are odd. The coordinate test is if xy is a point on the graph, then you have to have negative x and negative y in the graph, so you'd have to have both. The algebraic test is now we're going to replace x with negative x and y with negative y. If we get an equivalent equation, then we know it has origin symmetry. So for number 1, I am going to plug in negative for x and y. Now I'm going to simplify, so this would just be negative y equals negative x to the third power would be negative x cubed over 10. A negative and a negative here would become positive x. Then we have to divide by negative 1 right here, and that means we're dividing everything by negative 1, or multiplying by negative 1 to be the same thing. And then I would get y is equal to negative over negative becomes positive, so x cubed over 10, and then this becomes minus x. Is that the same as my original equation? It is. Since it's the same, that means that yes, this has origin symmetry. So let's go ahead and do number 2. I'm going to do the same thing. Replace x with negative x and y with negative y. So this becomes 4, and then negative x squared would just be x squared. It stays the same because it's to an even power. Negative y being squared becomes y squared, so 3y squared. And then a negative x times a negative y stays positive. And notice that this equation is equivalent to this equation. That means we have origin symmetry again. If we take a look at the graph that we have here, we want to complete the graph so it has origin symmetry. Remember, every point that you have, you change your x and your y values to be the opposite, and then that will make it have origin symmetry. So 0, 0 would stay here, and this point right here, which is 2, 2, would become negative 2, negative 2, and then you can kind of graph it from there, and the line would go down this way and stay forever. And that would be a graph that has origin symmetry. And for these graphs, it's not quite as easy as folding it across the or the y-axis or the x-axis. But again, you just replace your x with negative x and replace y with negative y. So let's go ahead and look at the next page, or your back page. And for this side, I'm going to write a little note at the bottom here. If, and you can write this at the top of your paper, if a graph has both x-axis and y-axis symmetry, then it also has origin symmetry. However, the converse of this is not true. That means that just because it has origin symmetry does not mean that it has both x-axis and y-axis symmetry. You can only say that if it has x-axis and y-axis symmetry, then it automatically has origin symmetry. On this page, what we're going to do is we're going to algebraically determine the symmetry. So we have to do those tests. Normally, this is a little bit easier if we first talk about even functions and odd functions. I'm going to look at this part on my paper that we have. An even function, when you have that, if you replace negative x into your function and get an equivalent statement out, that means you have symmetry with respect to the y-axis. For example, if we have f of x is equal to x to the fourth power plus x squared, and I replace x with negative x and get the same thing out, which in this case I would, because they're even powers, since f of negative x equals our original function, therefore we would have y-axis symmetry, and it would be an even function. If it's an odd function, when we replace negative x into the function, we would get negative of our function out. So for this equation here, if we did f of negative x, and we would get negative x cubed plus 2 times negative x. Negative x cubed would be negative x cubed, and this would become minus 2x. Notice that the signs have all changed, so that means that f of negative x equals the negative of our original function. This would mean that we would have symmetry with respect to the origin, and it would be an odd function. And an easier way to look at this is look at the powers of your equation. If you have all even powers, it's an even function, and even functions always have symmetry with respect to the y-axis. If you have odd powers, and one is this power for x to the first power, then you notice that you would have an odd function, which makes sense. So if we look at number 1, what I would do is look at this equation. Look at your powers. Notice your powers are both to an even number. So that means that if I were to replace x with negative x and plug it in, I would get an equivalent equation back out. So if I did y equals negative 2 times negative x to the fourth plus 3 times negative x squared, I get y equals negative 2x to the fourth plus 3x squared, and this is the same thing, which means that this has symmetry with respect to the y-axis. Oops. If I tried to replace my y with a negative for x-axis symmetry, it would change all of the signs in my equation, and that would not be an equivalent statement, so x-axis symmetry does not work, and that means that if x-axis symmetry doesn't work, then origin symmetry would also not work, because you would not get an equivalent equation back. And another way I think about this too is, remember, if you think about the smallest even graph that we have, y equals x squared, what does it look like? It looks like a parabola, and parabolas have symmetry with respect to the y-axis, and it's an even function. So that's usually how I remember. If I look at number 2, notice that I have an even power for my y and x is an odd power. That means that for this equation, if I try to do y-axis symmetry and replace x with negative x, it would not give me an equivalent statement back or equation back. So therefore, I know it's not going to be y-axis symmetry. That means that I'm probably going to try to do x-axis symmetry next. So do x-axis symmetry, remember you place y with negative y. And when I do this, I get y squared equals x plus 2, which is the same thing we started with. Because of that, I know that this is x-axis symmetry. And if I try to replace both x and both y, then the same thing happens because of that x is to an odd power. I would not get an equivalent equation back, therefore I know it cannot have origin symmetry. If I look at equation number 3, I notice that my y is being squared and my x's are all odd. So for this case, if I try to do y-axis symmetry and replace x with negative x, I would end up with a statement that's not equivalent to the beginning statement. If I replace y with a negative number, then since it's being squared, I would end up with x-axis symmetry again. And because of the first, what I said in the last equation, if I try to replace both x and y, I would not get the same equation back. So therefore, I know this one is also going to be x-axis symmetry. Now let's think about changing this equation. If I change something in this equation and I want to make it so that this equation, a similar equation would have origin symmetry, what would I have to change? Looking at it, I would have to change my y. If I change this right here so that it's not squared, and let's say I wrote the equation as, I'm going to do this as number 4, y equals negative x cubed over 2 plus 5x. Now, if I plug in a negative for x, it would change my sign, so it's not equivalent. If I plug negative in for y, it changes my sign, so it's not equivalent. If I plug negative in for x and y, my signs will all change, but then when I divide by -1 because of that negative y, I know that I would get an equivalent equation back, so this one would have origin symmetry. All right, so looking right here, it says if a rule for a function is a polynomial which all the terms have an even degree, then the function is even. A constant term has a degree of 0, which is we consider to be even. If a rule for the function is a polynomial for which all the terms have an odd degree, then the function is an odd function. Remember that even, again, is symmetric with respect to the y-axis. Odd is symmetry with respect to the origin. X-axis symmetry is neither even nor an odd function. And we're going to use, in order to tell if it's even or odd, you can look at the powers, but you still need to know this test where we replace right here negative x with into your function. If you get an equivalent statement back, then it's even, and you also need to know this one right here. It's important. Looking at this example, it says determine whether each function is even, odd, or neither. So we're going to do the test. Looking at this, I have a power of 10, 6, 2, and this is a constant, so this also means that it's even because it's to the 0 power. For x, we can write it in, but we don't need to. X, anything to the 0 power, remember, is just really equal to 1. So because of this, I know this equation is going to be an even function, but I still have to do my test. So to show my test, I would do f of negative x must equal the original function back. So let's do that. Negative x to the 10th power minus 3 times negative x to the 6th plus 2 times negative x squared minus 11. And when I do that, notice I would get f of negative x. This right here for the first equation would be equal to x to the 10th power, because anything negative to even power stays positive, minus, and this would be 3x to the 6th plus 2x squared minus 11. Plugging in the negative for x did not change my equation. That means that f of negative x equals f of x. And we just proved, using that this is an even function. So this is even. Now looking at b. For b, I would look at my degrees, or my powers. So I have 0, which is even. So this would be an even. 4, which would give me an even power. And the last one is 1, which is odd. Because of that, I'm already certain that this is going to be neither even nor odd function. That means if I were to do h of negative x, it would not be equal to, it would not be equal to h of x, nor would it be equal to the negative of the function. So this is neither. And just because it's neither even nor odd does not mean it has x-axis symmetry. Don't make that mistake. For c, if I look at this equation, I can see that the power of x for the first one is odd, the second one term is also odd, therefore I know it's going to be an odd function, but I still need to show g of negative x, plug it in, 5 over 7 negative x to the 5th power minus 2/3 negative x. When I do this, notice that my signs are going to change, so I get g of negative x is equal to negative 5 over 7 x to the 5th, and this would become plus 2/3 x. And notice that it's the opposite of what we had before, so that means that g of negative x is equal to negative of our function. Therefore, because of this right here, we have an odd function. For the next equation, we would do the same thing. If I look at my powers, I know they are all even, so I know that this is going to be an even function even before I do the test. But for the test, I would have to do h of negative x. When I plug in the negative x, I get negative x to the 4th power plus 5 over negative x squared minus 4. And when I do this, this is equal to our original function. So x to the 4th plus 5 over x squared minus 4. Therefore, h of negative x equals our original function, and it is even. And the last equation here, which is e, for this one I would do the same thing. Notice I have x cubed, and I also have x to the 1st power. So because I have two powers that are odd, I know this is going to be an odd function. And my test I would show would be q of negative x would have to be the opposite of q of x. So if I plug a negative in for x cubed here, this would make this sign negative and this sign negative. Then it would be the opposite of what our original equation was. Therefore, it would test out, and I would actually plug that into my equation to show that. If I go to my next paper, we're going to talk about operations of functions. And so really you need to do this part that we have down here. You're going to use this equation for f of x and this equation for g of x, and you want to perform all of these operations. For the first one, you're going to add the two functions together. So in this case, you would have 3x squared plus x, and then add that to 4x minus 2, and then you would need to combine like terms. So there are like terms with the x's. That means this would become 3x squared plus x plus 4x would give me plus 5x and then minus 2. So this would be my function. Then I would do f minus g, which you're going to have to do, multiply them, divide them. For d, e, and for I, notice that we're dividing by our functions. And whenever you are dividing by functions, you have to worry about your restrictions for your domain, because it says state the domain for d, e, and for I. Remember, how do you find the domain? You look for your red flags. Does it have any radicals in the equations? For both of these, it does not have a radical. But Since we are going to be dividing by our functions, that means we'll have variables in your denominator. So set your denominator not equal to 0, and that should help you find your domain. So make sure that you bring all this with you to class, and then we'll go ahead and talk about it and discuss it then.